see one new concept. Linearly independence of function and Wronskian of function. This concept is actually very important for higher study, also for higher study in applied mathematics. And this type of concept actually very important for any competitive exam, because this type of concept is obviously necessary for higher study. So this is important for any competitive exam. We all of us know in linear algebra, I have seen what is the linearly dependence and independence of vector. Today I will say linearly independence of function. Actually here the vector has a denoted as a function, and this is similar to before as a linear algebra. We all of us know algebra what is the linearly dependence and independence of vector. If we consider two functions, then in particular two functions y1x and y2x are called linearly dependent on some interval I if they are proportional on I. That means y1 equal to ky2 or y2 equal to ky1. And if the function y1x and y2x are not proportional on the interval I, then they are called linearly independent set the interval I. This is the concept of linearly dependent and independent of a function. For example, if we consider y1x equal to x and y2x equal to mod x, then obviously these two functions are linearly independent on the interval minus infinity to infinity. Let's see the picture. Y1x equal to x means obviously this function y1x equal to x, and y2x equal to obviously mod x. And notice these two functions are not multiple of each other. So obviously these two functions are linearly independent on the set minus infinity to infinity, because y2x equal to mod x means x when x greater than 0 and minus x when x less than 0. So we cannot write y1x as a multiple of y2x. So y1 and y2 are both linearly independent on the set minus infinity to infinity. Okay. Example, if we consider two functions sin x and cos x, they are both linearly independent, because similarly they are not multiple of each other. But if we consider x square and 2x square, these two functions, then 2x square is multiple of 2 times x square. That means these two functions are linearly dependent. I have considered two functions. I have considered when two functions be linearly dependent or independent. Actually, in general, a set of functions y1x, y2x, ynx is called linearly dependent on the interval I if their x is constant c1, c2, cn, not all 0, such that c1 y1x plus c2 y2x up to cn ynx equal to 0. Here, since c1, c2, cn are not all 0, that means y1x, y2x, ynx is actually the multiple of each other. And a set of functions y1x, y2x, ynx are called linearly independent on an interval if the only constant function for which c1 y1x plus c2 y2x up to cn y1x equal to 0. And this relation is true for all x in I, and c1 equal to c2 equal to up to cn equal to 0. Then we can tell in general y1x, y2x, ynx are linearly independent function. Okay. I hope my all viewers have understood this concept. Now I will consider 4 function. Now I will see 4 function y1 x equal to cos square x, y2 x equal to sin square x, y3 x equal to sec square x and y4 x equal to tan square x are linearly dependent on the interval minus pi over 2 to pi over 2. For this, consider c1 cos square x plus c2 sin square x plus c3 sec square x plus c4 tan square x equal to 0. Here consider c1 equal to 1, c2 equal to 1, c3 equal to minus 1 and c4 equal to 1. Then I will get cos square x plus sin square x minus sec square x plus tan square x. And this value is obviously equal to 1 minus sec square x means 1 plus tan square x plus tan square x. Then this value would be obviously 0. So I have got non-zero c1, c2, c3. For this, the value of the function is 0. Therefore, obviously this function is linearly dependent on the interval minus pi over 2 to pi over 2. Okay. Next I will say one function which is linearly independent. The function e to the power x, e to the power x, 2x, e to the power 3x are linearly independent on the interval minus infinity to infinity. For this c1 e to the power x plus c2 e to the power 2x plus c3 e to the power 3x equal to 0. For linearly independent, we have to prove this c1, c2, c3 both are 0 on the interval minus infinity to infinity. And we know that e to the power x always greater than 0 for all x. Now divide it, the equation 1 by e to the power x. Then I will get c1 plus c2 e to the power x plus c3 e to the power 2x equal to 0. And for easy calculation, now differentiate this equation with respect to x. Then I will get, now differentiating with respect to x, then this would be c2 e to the power x plus 2c3 e to the power 2x. Now again divide e to the power x in both sides, then I will get c2 plus 2c3 e to the power x equal to 0. Now again differentiate this equation with respect to x. Then I will get 2c3 e to the power x equal to 0. And since e to the power x greater than 0, that means obviously c3 equal to 0. And if c3 equal to 0, then that implies c2 equal to 0. And since c3 and c2 equal to 0, that implies c1 equal to 0. Therefore, I have got c1 equal to c2 equal to c3 equal to 0. But this calculation is broad calculation. For easy calculation, there exists a nice method, Wronskian. You can tell easily what is Wronskian. Wronskian is, suppose each of the function y1x, y2x, ynx possesses at least n minus 1 derivatives. Then the following determinant is called Wronskian of this n function. Actually, Wronskian of y1, y2, yn means determinant of this matrix whose first row would be y1, y2, yn, second row would be y1 prime, y2 prime, yn prime, and nth row would be y1 to the power n minus 1, y2 to the power n minus 1, yn to the power n minus 1, that means n minus 1 derivative of the function y1, y2, yn. And determinant of this matrix is Wronskian. By Wronskian, we can tell a function be linearly dependent or independent. But notice here very interesting thing. First fact, if y1 and y2 are linearly dependent, then we can tell Wronskian of y1, y2 equal to 0. Because here y1, y2 linearly dependent, that means obviously y1 would be multiple of other, then Wronskian means obviously y1, y2, y1 prime, y2 prime. Just put the value, then this would be y1 means cy2, y2, cy2 prime, y2 prime, and this value is equal to 0. So, if y1, y2 is linearly dependent, then Wronskian of y1, y2 always equal to 0. If Wronskian of y1, y2 not equal to 0 for some x in the interval, then we can tell y1x and y2x are linearly independent on this interval. So we can tell sin x cos x is linearly independent because Wronskian of y1, y2, here y1 is sin x and y2 is cos x, is minus 1, which is not equal to 0. So, and this is true for all x belongs to real number. So, sin x cos x are linearly independent in whole real line. If you find the Wronskian of e to the power x, e to the power 2x, e to the power 3x, you will see this Wronskian always would be not equal to 0. And this is very easy method. By this Wronskian, we can tell this function is linearly independent on the interval minus infinity to infinity. I hope my all viewers understood how by Wronskian we can tell a function be linearly dependent or independent. But notice here very interesting thing. If y1 and y function is linearly dependent, then we can tell Wronskian of y1, y2 equal to 0. But converse of this theorem is not true. There are many functions whose Wronskian is equal to 0, but still the function is linearly independent. See one example. Now notice these two functions y1x equal to x mod x and y2x equal to x square. On this interval x belongs to minus 1 to 1. If you find this Wronskian, then this value would be 0. But I will see these two functions are linearly independent. For this, c1 x mod x plus c2 x square equal to 0. We have to prove c1 c2 equal to 0 for linearly independent. For this relation is true for all x belongs to minus 1 to 1. So consider x equal to half. Then I will get c1 over 4 plus c2 over 4 equal to 0. That implies c1 c2 equal to 0. And consider x equal to minus half. That imply minus c1 by 4 plus c2 over 4 equal to 0. That imply minus c1 plus c2 equal to 0. And from these two relation, that implies c1 equal to c2 equal to 0. And since I have got c1 equal to c2 equal to 0, that means our given function x mod x and x square are linearly independent. But I have got Wronskian is equal to 0. Here, this function is linearly independent on the interval minus 1 to 1. But if we consider 2 comma 1, then this value would be, then these two functions y1 and y2 would be linearly dependent, because in 2 1 this is positive, always would be positive, this value would be positive, and this value is actually x square, and x square y2 is also x square. So this two function is actually equal. So I hope my all viewers have understood why linearly dependence and independency. I have told you it is depends on the interval. Okay? Converse of this theorem is not true, and this converse would be true when this would be differential equation. There exists a nice theorem in differential equation. This differential equation y double prime plus px y prime x plus qx yx. We all of us know this is the differential equation where p and q are continuous function on the x over the interval I. Always p and q would be continuous function over the interval I. Then if y1 and y2 be the solution of this differential equation, and this solution would be linearly dependent on this interval I. If this solution are linearly dependent, then obviously Wronskian of y1, y2 equal to 0 at some point x0 belongs to I. And this condition is if and only if condition. If Wronskian of y1, y2 equal to 0, where y1, y2 be the solution of this differential equation, then we can tell these two solutions are linearly dependent on the set I. Furthermore, if Wronskian equal to 0 at some point x0, then obviously Wronskian is identically equal to 0 on the set I. There exists one x0 belongs to interval I, where Wronskian not equal to 0, then that imply obviously these two solutions are linearly independent. And in differential equation, this condition is if and only if condition. That means if y1, y2 are solution which are linearly independent, then obviously Wronskian not equal to 0 on this interval. Okay? I will see one interesting question which had come IIT JAM 2009 exam. The question is f and g. Consider this is be the function from -1, 1 to r, where fx equal to x cube and gx equal to x square mod x. Then option 1, f and g are linearly independent on the set -1 to 1. Option 2, f and g are linearly dependent on the set -1 to 1. Option 3, fx g prime x minus f prime x gx is not identically 0 on the set -1 to 1. And option 4, there exists a continuous function px and qx such that fg satisfying the equation y double prime plus py dash plus qy equal to 0. I hope my all viewers have understood this question easily. This type of question I have defined few minutes ago. I have seen these two functions y1x equal to x mod x and y2x equal to x square. In this function Wronskian is equal to 0, but these two functions are linearly independent on the interval -1 to 1. This function is linearly independent on the set -1 to 1. But Wronskian is identically 0. So option 3 also wrong option, option 2 also wrong option, option 4 also wrong option. Because if there exists such type of differential equation where p and q are both continuous function, then Wronskian equal to 0, that means obviously the function is linearly dependent. But here this function is linearly independent. So there cannot exist this type of differential equation. I hope my all viewers have understood this question clearly. At first I will highly recommend you at first see the whole video with pay attention, then you will understand this question easily. Today I will stop here. In my next video I will discuss and when a differential equation be exists, unique solution, infinitely many solution or no solution. This type of question very important for higher study. So, in my next video, I will discuss this type of concept. Okay? See you soon. Stay safe and stay positive always. Thank you so much.